All right, let's talk about one of the biggest, most profound puzzles in all of physics. Seriously, this is a cosmic whodunit that basically challenges everything we thought we knew about the universe. So let's get right into it. And this right here, this is the core of the whole mystery. Is there some hidden rule in nature, some kind of cosmic bodyguard protecting the Higgs boson? Or are we getting a peek behind the curtain, a glimpse into hidden layers of space-time itself? The answer could literally change everything. You know, every great detective story kicks off with a clue that just feels wrong, something that doesn't fit. And for physicists, that clue was a particle they've been chasing for like 50 years, the Higgs boson.
So, flash forward to 2012. The folks at the Large Hadron Collider finally catch their prize. They put it on the cosmic scale, and they get a number, 125 giga-electron volts, or GeV for short. This was massive news. Nobel Prizes were handed out, champagne was popped. But for the theorists, that number, 125 GeV, wasn't a cause for celebration. It was a huge, huge problem.
I know what you're thinking. 125 GeV sounds pretty hefty, right? But in the strange world of theoretical physics, that's shockingly light. It's like our best theories, the ones that work for everything else, predicted the Higgs should be trillions of times heavier. It's like expecting to lift a bowling ball and instead finding a single feather. The difference is just that staggering. So the real question becomes, why? What is holding its weight down?
Okay, to really get why this tiny weight is such a big deal, we gotta look at the big picture. We need to compare it to the other fundamental forces that run the universe. This isn't just a quirky little detail about one particle. This goes to the very heart of how reality is put together.
And this, my friends, is what physicists call the hierarchy problem. It's a fancy name for a simple but profound question. See, you've got the electroweak force, where the Higgs hangs out, ticking along at around 246 GeV. But then you have gravity, which operates on a completely different level, the Planck scale. We're talking 10 to the power of 19 GeV. That's a 1 with 19 zeros after it. So, why the gap? Why is gravity so ridiculously weak compared to the other forces? It just makes no sense.
This chart just says it all, doesn't it? That little sliver on the left, that's our electroweak scale. The other bar, well, that's the Planck scale, and it just shoots off into infinity. The gap is almost laughably big. Now here's where it gets really weird. In the quantum realm, the Higgs is constantly interacting with all these other virtual particles. These interactions should add a ton of energy, a ton of mass to the Higgs. The immense energy of that Planck scale should be yanking the Higgs mass all the way up there, but it's not. It just stays put. Something's not adding up.
So what do you do when the math breaks? Well, physicists put on their detective hats. They came up with a whole lineup of theoretical suspects. Really beautiful, elegant, new ideas that could possibly explain this whole mess. Theories that could tell us how the Higgs is keeping its weight down.
Let's check out the two main culprits in the lineup. First up, we have supersymmetry, or SUSY for short. The idea is that every particle we know has a secret, heavier twin, a superpartner. And get this, the math works out so that the mass-adding effects from regular particles are perfectly canceled out by these new superpartners. It's like cosmic accounting that leaves the Higgs nice and light. Then you've got the idea of extra dimensions. This theory says that gravity isn't actually weak. It just looks weak to us because it's spreading its influence across other tiny hidden dimensions. If most of gravity's punch is happening elsewhere, it wouldn't be strong enough in our dimension to make the Higgs super heavy.
Okay, so we've got our suspects. Now it's time to find some hard evidence. This is where the Large Hadron Collider comes in. This incredible machine was basically built for this. Its main mission was to smash particles together and hunt for clues, to find some proof that one of these wild theories was actually right.
But here's the twist in the story. After years and years of running the LHC, creating quadrillions of collisions, sifting through galaxies of data, they found absolutely nothing. Not a peep. All our prime suspects, they've got perfect alibis. The trail just went dead.
I mean it. The crime scene was wiped clean. Those super partners from Supersymmetry? Nowhere to be found. Any weird energy signals that might point to extra dimensions? Nope, nothing. Even the other, more out there ideas, totally empty-handed. This is a huge problem. This lack of evidence is almost worse than finding something contradictory. It's just silence.
So what happens now?
What do you do when all your best leads, your most elegant theories, just evaporate? Well, you're forced to consider some, let's say, weirder explanations. Ideas that feel less like physics and more like philosophy. And honestly, a lot of scientists really don't like where this is going.
And that brings us to this really controversial idea called the anthropic principle. The thinking goes something like this. Maybe there is no deep, elegant reason for the Higgs mass. Maybe we live in a multiverse with a bajillion different universes, and in each one, the laws of physics are slightly different. Most of them are probably total duds. But we just happen to live in one of the universes where the Higgs mass is exactly this value, because if it were any different, well, we wouldn't be here to even ask the question. To a lot of physicists, this feels like throwing in the towel. It's like saying we won the cosmic lottery instead of finding an actual reason.
Look, at the end of the day, this isn't just about one number for one particle. The hierarchy problem is a giant crack running right through the foundation of our best theory of everything, the Standard Model. It's a huge flashing sign that says you're missing something big. Solving this isn't just about cleaning up a detail. It's about discovering the next fundamental layer of reality. The case might have gone cold for now, but you can be sure the investigation is far from over.